So, the plan for the first lecture is to tell you what is classical field theory. So, what we will do is we will start with the familiar. Hopefully, all of you know what classical mechanics is. So, let us just review classical mechanics. So, you start in high school where you learn fine, we usually write things like F equal to ma, and this is Newton's equations. But as you move ahead, you realize that there are more sophisticated ways of handling things. For instance, you learn about Lagrangians and Hamiltonian formulations of mechanics. The advantage of these formalisms is that they are much more general than Newton's equations and subsume them. So, in some sense, if you choose a particular Lagrangian or a particular Hamiltonian, you can recover Newton's equations. And most of the forces in mechanics that one looks at, they are usually velocity independent. Okay. And of course, friction is an example of a force which is velocity dependent, it is dissipative. But there is one more velocity dependent force which is not dissipative, it is conservative. What is that? The electromagnetic force. Okay, especially the magnetic force, it's a force which is unlike any other force, it is velocity dependent, but nevertheless it is conservative. Okay. And so, this is a very nice example which can be completely dealt with in the Lagrangian formalism. Another set of a nice system, the reason to use Lagrangian is that you can handle constraints can be handled. Okay, not all kinds of constraints, but some classes of constraints can be handled in this formalism. Okay. So, for instance, a simple exercise for you, and I will keep giving exercises which you should go home and check, is to take a Lagrangian for a 3-dimensional particle which would be a Lagrangian of this form, where A is the vector potential okay. So, now you see we have a Lagrangian here. If this were not there, it is a free particle, but this is a term which has a velocity dependent potential, and you can go back and check that you end up getting equations of motion which is not this, but f. So, the equations would be m x double dot equal to q into v cross b. Okay. So, go back and check this equation, and so here is a case where we can nicely handle this, and it can also be handled in the Hamiltonian formalism. Okay. So, the reason to look at general formulations is that as you go into situations where your normal instinct does not work, it is better to have abstract methods of handling things. And the nice thing about this particular formulation we will see is that it generalizes naturally to classical field theory, and you can incorporate a whole bunch of things as we will see. So, let us just sort of do a quick review of the Lagrangian formulation, and that is usually done by something called the principle of least action. Okay. So, the input is something called the Lagrangian, which we have already discussed, which is a function of coordinates and velocities. So, now qi here, let us say there are n degrees of freedom in your system, there will be that many generalized coordinates, and as many generalized velocities. Okay. And in principle this could also have an explicit dependence on time. Okay. So, this is what we will call explicit time dependence. Okay. As opposed to implicit time dependence, because both coordinates and velocity can have time dependence through their arguments, they can vary with time. Okay. So, this we will say are explicit time dependent, while this gives you implicit So, for instance, if you want to know how this object the Lagrangian changes with time, or you want to take its time derivative, you do in multivariate calculus, you will compute something called the total derivative, which has several pieces. One is the explicit time dependence, which you write by a partial derivative, and then you look at the various arguments into dq by dt, which I write as qi dot plus okay. So, the first term comes from the explicit time dependence, while the next two terms come from the implicit time dependence on qi gives you this term, while qi dot gives you this term. Okay. So, this is what is a statement of taking the total time derivative. So, if you say that if the Lagrangian has no explicit time dependence, then what would you say? Then we would say then the mathematical way of stating that is dl by dt equal to 0, the partial derivatives with respect to time. But of course, if you look at the total time derivative, it can change. Okay. And then there is the notion of a particle trajectory, okay, which is very simple. It just tells you, if you give me a system with some generalized coordinates, you tell me how qi varies as a function of time. Okay. So, this is just the time evolution of the system is given by some function qi as a function of t. So, if you have 1 degree of freedom, then I can draw a nice picture. So, let us do that, q of t versus t, and let us say you have some initial time t1 and at some later time t2, let us say we only observed during this range the particle started somewhere here and did something and ended here. So, this would be an example of a particle or a system trajectory. Let us call it a system, because it need not be a system of particles, even though I called it particle here, but it's, or just simply call it trajectory. Okay. And the key point here is that the Lagrangian tells you what the trajectory of the system would be. gives you the dynamics of the system. Okay. So, in principle I can keep drawing different kinds of trajectories. Let us change color for a moment. Here is another one, but the question is, what is the trajectory followed by the system, the actual trajectory, and that is determined through the Lagrangian via the principle of least action. So, let us see how that is done. So, it should tell you among the various trajectories, so first let us define something called the action. The action takes as its input. Now, for the rest of this lecture I will, for simplicity, I will just choose 1 degree of freedom. You take so it is something which takes as input the trajectory or of the system and gives you output a number. Okay. And that number, so let us say, okay, so this is the action. Okay. So, this is similar to a function, except that as its argument it is taking a trajectory which is another function or many functions depending on how many degrees of freedom. So, this is an example, it is called the action functional. Okay. So, just recall that a function is a map from some domain, say some from function from some domain to reals. Okay. So, if x belongs to this thing, it will give you f of x, which is the number, but a functional. So, this is a function, okay, while a functional like s, it takes as input trajectory, all trajectories. So, this should be space of trajectories, but to again to some real number. Okay. So, in that sense it is exactly similar to this. You give it as input a trajectory, output is a number, okay, and that is what, okay, and this is a functional. So, example is exactly this. You take q of t and then you get s of q of t. So, now if somebody comes and gives you a function, you would like to ask, generally it is sort of a first course in calculus, you are asked to find out its extrema, in other words points which are maximum, where the function takes a maximum value, local maximum or a local minimum. So, if you have a function, so the way you determine for a function, extrema are, so we will say f of x are determined by solving okay, and then you use the second derivative to determine whether it's a minimum, local minimum or a local maximum. Global would require you to compare across these things. Okay. So, now there is another way of understanding this thing. So, the derivative always requires you to compare values to nearby values, and so you could think of it as asking this, going back to the discrete limit, which is like limit some epsilon tends to 0, f of x plus epsilon minus f of x divided by epsilon, okay, should tend to 0. Okay. But you can do it in a slightly different manner, in a formal manner. Think of epsilon as a small number, okay, and what you are doing is, if you did f of x plus epsilon minus f of x, you know that there is a full Taylor series, but the key point here is it is 0 times epsilon plus order epsilon square. This is another way of stating it. You just compare two neighboring values of function, and every time it hits a 0 to first order in epsilon, that is equivalent to doing this. Okay. It is the same statement, it is not anything different, because in as much as you can Taylor expand a function, the coefficient of epsilon is indeed the first derivative for smooth functions. So we will assume that the function is smooth. Okay. So the point here is that the principle of least action tells you that you should choose the trajectory such that the action takes a minimum value. So the first step to solving that is to ask what it should take an extremal value. Okay. So the problem is exactly identical to this, except here what did we do to find the thing? You keep changing the value of x and ask where this is true. Okay. So a similar question to do out here is, so the analog of x here is a trajectory, so you have to keep changing trajectories, and we need to ask when this variation, so we will just call this delta f, is 0 to first order. That is all. Okay. So let us see how that goes. So the trajectory of the system is such that the action functional is minimized. I would say extremized, because okay. So now what we will do is to do the same thing which we did here, but we will work it out in this particular form. Okay. So let us see how that goes. So let us take one degree of freedom from some initial time to some final time, dt of L of q of t. For once I will put all the arguments, maybe it has even explicit time dependence, that is okay. Okay. So now what is it we should do? We should take two neighboring trajectories. So the question is, what does it mean for two trajectories to be nearby? So when we talked of function, we know what it means. There is a notion of distance. Okay. And but here what we are doing is we are talking about the space of trajectories. Is there a natural distance to them? These are questions to which I think the general answer is not known, but you can think of a distance by saying, okay, let's consider, so an example of a distance of two trajectories. So d, so let us say q1 of t and q2 of t are two trajectories which are nearby. Okay. So let me, for instance, define them to be something like this. Square. Okay. This is, I am not saying this should be the distance, but here at least I have some notion when the two trajectories coincide, this becomes 0, and intuitively at least this captures something like that. Okay. But what we will do is what is called formal stuff, where we will just look at the coefficient of the guy, which is we will write some formal parameter epsilon. Okay. The statement formal here means that we do not worry too much about issues of convergence, which I must tell you is important, but not for this purpose. Okay. So formal means that we do not worry about convergence issues. Okay, so what we are going to do is we will take two trajectories, one we will call that q1 of t and a second one which I will call q2 of t, which I will write as q1 of t plus epsilon some other function of t. So, let us just call it g of t, or even better I just call this delta q. Okay, the important thing here is epsilon is my bookkeeping parameter and I need to expand things to first order in epsilon. Okay, so, what I would do is define delta s to be s, you evaluate it for the trajectory q2 of t minus s q1 of t. Okay. So, as it stands it is just a difference of two numbers, but next step what I will do is to substitute for q2 in this form and use the explicit formula that I have. Okay. So, all I have done is to take the definition out here. Now, you may wonder is delta q dot something independent? The answer is no. I will just assume this is a smooth function. I take q2 dot is just q1 dot plus epsilon delta q dot. Okay. Now, the important point here to notice is that the object in the square bracket in this curly brackets in curly braces is at some time t. This is a number, but the argument here if you is at some particular t in between t1 and t2. Okay. So, it is also a very useful device to take time and make it discrete. I will not do that, but you make it discrete so that this integral becomes a summation. Okay. So, you will see that this object in brackets there is one term for every time step. Okay, and for every time step there is a delta q, and for each time step the delta q's are independent of each other, because I could do the following thing. Coming back to this picture, and let us say that we choose this is the trajectory q1 of t, and let us say I want to do q2 of t, but I could do things like, let us say that I make q2 only different in two different neighborhoods just for, so it is the same as here, but maybe somewhere here it is slightly off, then it comes back to this, follows this, some other space it goes off and comes back. Okay, and I can adjust it in whichever way I want, and you can see that I can make this peak. I can look, so the point here is that this delta q is completely independent of this. More generally, the delta q's at any two different time instances are independent of each other. Okay, and the mathematical way to state that is that delta q of t1 and delta q of t2 are actually independent of each other, and except when they are the same it will be 1. But this is when you are discrete it would be 1, but when you are in the continuum you would replace it by the Dirac delta function. So, this is exactly what I just told you. Says that any two instances delta q those things are independent of each other. Okay. So, this is in some sense the most important formula which captures this sort of trivial but important statement. Okay. So, now we can go ahead and look at this thing and expand it. So, now we look at what we are doing is we are looking at what is inside the square, inside the braces, and that is at a given time, and we are going to compare these two numbers. So, delta s, so now you can see that in this thing there are two terms which will contribute to the change in L, and so we can just use normal, you think of L as a function of q1 and q1 dot, two independent variables, okay, and so the 0th order piece cancels. So I will only write out 1 times delta 2 sorry dl by d2 times the change, so that is q2, so delta q2, delta q is nothing but q2 minus q1, so that is epsilon okay. I am just keeping this, reminding you that it is for independent for every time, okay. Of course, plus order epsilon square, we are not bothered about that at this point. Okay. So now you can see that since since this has to hold for every time step, this thing, so we want to find the extrema that would, in other words, we need to solve the analog of delta f equal to 0. So we need to check whether what we want is whether when is delta s equal to 0. This is the question we would like to answer, but as I pointed out, for each time step they are different. So this can happen only when every term vanishes separately for each time. So the curly bracket should be 0 by itself, but we will do a little bit, we will do one more step before we do that, and we will use the fact that delta q dot is nothing but d by dt of delta q, and we will integrate by parts and rewrite this thing. So I am jumping some steps because I am sure all of you have seen this before, and there is a surface term which is a total derivative piece, that is okay. So we have two terms, one is the order epsilon, oh there is an epsilon even here, okay, and we want this thing to be 0, and since this is a total derivative I can integrate, this will only get contributions from the two endpoints. So let us look at when t is not either t1 or t2, then this term does not contribute, so only these terms contribute, and you can see that we get dl delta s equal to 0 implies dl by dq okay. But what about t equal to t1 and t2? That has, so there what we would do is, if we want we choose delta q at t1 equal to 0 and delta q at t2 equal to 0, okay. So this is what we will call a boundary condition. In other words, we do not look at arbitrary trajectories, we look at space of trajectories such that the initial and the final points are given, okay. And once we do that, all we need to do is to solve this equation. This is the Euler-Lagrange equation of motion. Equation of motion, EOM is something I will keep using, and so this is how the principle of least action works, okay. Are there any questions? The advantage of this picture is that the transition to quantum mechanics can be seen in a very easy manner. Okay. So, what about quantum mechanics? Actually, one is not really done with this. So, you would look for solutions of this, but now the question is, like any function, there could be many extrema, some of them will be minima, some of them will be maxima. So, now so in physical systems there is a notion of stability, if you wish, and so that is the same as saying that you need to pick the situations where the energy is minimized or whatever. So, that is something which you need to check. You need to check if your solution, which I mean this is only a statement of the first derivative. So, there is an analog of checking for the second derivative, okay. And there will be instances in which we will consider different solutions, classes of solutions, for whatever reason we will see, we will consider them, and they will be inequivalent in a particular sense, that if you started out with a configuration, it could never go into the other. There is some sort of topological quantum number or something which will stop it from going. So, Feynman's description of quantum mechanics is as follows. He says that suppose your system is at some state at initial time, it's localized in space at this point q of t1, and you want to know what is the probability amplitude that the system will in the state in some other state, some value. So, let us say yeah, q at t1 in some other value at time q2. So, q at t1 and q at t2 are numbers, okay, which is exactly like your initial and your final conditions. It is localized out there, okay. And the answer is, so usually that is given by some sort of an amplitude. So, the probability amplitude, not probability, of being at q at t2 given that it was at q at t1 is up to some normalization proportional to the sum over all trajectories with a weight factor which is s. Okay. So, the statement here is that actually all trajectories contribute to the. So, you may ask, what is so special about this guy, about the solution of this. Okay. So, roughly speaking, this gives the maximum contribution. So, the classical trajectories dominate the above, and the way to see that is, roughly speaking, the classical limit is taking h bar going to 0. Okay. So, in other words, this the denominator is going to 0. So, now unless this was at its lowest value, one point is that I can always adjust the action such that its lowest value is 0. Okay. That so we can just mod out by some constant phase shift, and so then the dominator, it will go to 1 only when this is at its lowest value, which we have set to 0, but for anything else it will be fluctuating wildly, and so his argument is that they cancel away. Okay. But if h bar, if you want to know the h bar corrections, then you have to take the contribution of all the trajectories. Okay. So, in principle this is a very complicated calculation to do for an arbitrary action, but notionally it gives you, I mean for simple examples you can actually carry this out exactly and show that it gives you answers which are identical to what you would have done using say the Schrodinger or the Heisenberg picture in your quantum mechanics course. So, we are sort of now ready to sort of understand what classical field theory is about. So, in usual classical mechanics usually you have only a certain number of finite number of degrees of freedom, okay, countable or whatever you say, okay. And so the thing is how does one handle situations where the degrees of freedom classically itself are given by a field. So, let us look at examples of a field. Examples of a field for instance would be the temperature in this room. So, okay. So, at every point in this thing there is a temperature. So, if I want to discuss the change in of the temperature in this room, I need to handle the fact that the temperature need not be a constant here, it could be one value near the AC and one value very far from the AC. Okay. So, this could change with this thing, of course it is also a function of time. Similarly, the electric field, okay, it has roughly 3 times the degrees of freedom as this, because at every spatial point this thing has a scalar degree of freedom while this has a vector degree of freedom. Okay. So, now the point here is that we have infinite degrees of freedom like this, okay. But even if you take a ideal gas, notionally it has an Avogadro number which is 6 into 10 power 23 molecules. So, 3 times that, it has that many degrees of freedom. But there is a difference between that setup and this, and that is the notion of 2 neighboring points. Here we understand 2 degrees of freedom being close to each other, while if you have an ideal gas, there you have many different particles, and there is no notion of 2 particles being close to each other or 2 degrees of freedom being close, there is nothing like that. So, the difference is there is really extra data which is coming out here, that there is some physical distance that is there between the degrees of freedom. So, you need so there is a notion of what we will call locality in a field. In particular, we know that if I want to discuss the electric field in this room, okay, I do not really need to worry about things which are very far away. In the next galaxy I do not need to solve that problem. Okay. So, in other words, that there is some decoupling. So, what you expect is objects which are close to each other only interact, not something which is. So, we do not want to have things where we have action at a distance. Somehow apparently Saturn can affect our lives, that is what people say, but that is action at a distance, that is something which is unscientific and we do not put that in. Okay. So, we will, this is something which we have to incorporate. So, it is not just a question of saying that I just go back, and if you remember I said if there are many of them you will put something like this, put an index I, and you said I let it be infinite. Okay. That will really not be not capture this issue of locality. So, we need to somehow put this into the setup, and this is really the one of the key thing. Another thing which we need is the notion of causality. Causality is that you want cause to precede effect. Okay. So, the thing is that if you did something, so let us say you have a system, and let's say we take another continuum system is like a bucket of water, and then you there the velocity field, if you wish, is a field. It's again like this. At every point you have this thing, and you go ahead and do a local disturbance somewhere. You know that that takes some time to propagate. So somehow we should also be able to incorporate causality also, that is cause precedes effect. And there will be more things. There will be things like symmetries in the problem. This is something which we will understand later. We need to incorporate some of them. Okay. So you can see that it is not just a question of taking the number of degrees of freedom to become infinite, but rather what you want to do is to somehow be able to incorporate these things. Okay. And this is something which we will learn how to do, but right now we are sort of ready to draw blocks. So classical field theory is just the classical mechanics of fields, that is all. So let us draw some boxes. So we saw classical mechanics, and so there we saw that there was an action, and then the extrema of the action gave you the classical trajectory of the system, and in quantum mechanics all trajectories were sampled. So you get something like this, which we will call quantum mechanics. And we saw roughly that h bar tending to 0 gives you this, the arrow this way. And now, so this is just finite number of okay. So you go to infinite degrees of freedom, and then we need to incorporate things like locality. We don't know how to do these things yet, causality, so on and so forth, but you get the classical mechanics of fields, and this is something which we will call classical field theory. Okay. This will more or less conclude my lecture, but obviously there is a box missing, because I could do the same thing out here. Okay. And so we could do a similar thing, and this box is called quantum field theory. So again, there is a similar arrow to this. Okay. Again, this would be h bar tending to 0, and so in this course, of course, we will not be doing quantum field theory, but on and off I will keep referring to quantum effects, just to show you that there is quite a bit, and this is a very rich subject and requires a lot of study. But what we will be doing is doing only classical field theory, and maybe in your next course you would be doing quantum field theory. So this is a good point to, for me to stop and ask you questions. Are there any questions? Okay. So in the next few minutes I am going to sort of discuss symmetries, and we will do that in the classical mechanics setting, but in the next lecture we will start formulating what is the meaning of a symmetry, etc. But there is already something which you know. What is special about time independent Lagrangians? That means there is no explicit time dependence. Does anybody know what is special about time independent Lagrangians which do not have explicit time dependence? They have a constant of motion. Okay. That means let d be some quantity, its derivative. So, it is some function of q, q dot or whatever, which is 0 for all time. So, let me ask again, what is the constant of motion? What would you call something which does not change with the trajectory, and this is the Lagrangian is time dependent, time independent, has no explicit time dependence. It is usually called the energy. So, in this case d you can show is p q dot. Okay. This is the energy. Okay. This is not the Hamiltonian, okay, for the simple reason that the Hamiltonian is a function of two different variables. So, d here is only a function of q's and the q dots. Okay. And just one more comment, that what we will be doing is that we will use, whenever an index is repeated, we sum over. I do not write summation over I. So, here this is the Einstein summation convention. So, this I sum over all I. Okay. So, this is an example of a symmetry, and the symmetry here is time translation invariance. Does not matter when you do your measurement, your action, if you translate would give you the same number. If there was explicit time dependence, it matters the when you measure the action, what were the limits, the T1 and T2. It is not you can't shift things away and you get okay. So, you do get a symmetry. This is an example of a symmetry. Okay. So, what we will see here in this course is that there is an intimate relation between symmetries and conserved quantities. Okay. And so, we will have to go through a procedure of asking what is the symmetry, what is the best way to define it, etc., and that is what we are going to do in the next lecture. And this will take about 2 to 3 lectures, and really the formulation of classical field theory will happen only after 3 or 4 lectures. So, you have to be a little bit patient. We will make a small mathematical detour and come back to that. Okay.